Uh, okay, everyone. We are happy to have Justin David telling us about precision tests of bulk entanglement entropy. We can start.
Okay, thank you for the organizers for giving me this invitation. So I'll be talking about this couple of works actually done with a student and a couple of postdocs who are here in the audience. Let me begin with an introduction. So as this meeting is all about, one of the central themes in this meeting is the Takayanagi formula, and it provides an expression for the entanglement across subregions. I guess all of us know, but let me just state it, and which is intrinsically a quantum object in terms of classical quantities like the area of the minimal surface. So let's just, to put it in context, let's write down the formula. So here's the formula, and in principle, it can be tested against CFT calculation in principle. So here's the CFT entanglement across a particular subregion A, and then this is the area of the minimal surface. In this particular case, I'll be focusing on ADS3, and so therefore it'll be a geodesic length. That's the length, and this is the Newton's constant. It's very much like the black hole entropy formula. Now, this formula admits a well-known correction or a modification at G Newton to the zeroth order, in which it is modified, and it's an important modification, modification by Faulkner, Lukovich, and Maldacena, and in which there is an added term in which basically is an entanglement of the bulk across that region sigma A. So let me give you the geometry again. So this is, say, ADS3 sliced at t is equal to 0. This is the minimal geodesic, and this gamma A will be the length of the geodesic, for instance. The gamma A is the geodesic, which divides the two regions, sigma A and sigma A bar, and we have to trace over this. And this 2 pi x is the circle or arc length along the boundary. So this is sort of the geometry. I think this geometry is simple enough for all the people in this meeting. So the FLM proposal and its generalizations, I mean, a lot of discussions might have been there in this meeting, has played an important role in this understanding of the quantum gravity and information paradox. And the generalization involved extending the formula to any subregion of gravity and the notion of the quantum extremal surface. Now, the FLM formula is within the framework of ADS-CFT, and therefore it can be principle tested against evaluating entanglement of various states in the CFT and comparing them against the result from the FLM formula. So apart from the verification of FLM formula, okay, well, I mean, because it has been used so much, you would ask, okay, what's the point of verifying this whole formula? So apart from that, what can you learn from it? So by doing this, we will learn to develop techniques to study excited states in CFT. Using the replica trick, this will involve, as you will see, evaluating two endpoint functions, taking the n going to one limit and so on. And it will develop techniques to evaluate this S bulk, which is sort of interesting because that is not done usually. And so this involves performing traces in the bulk geometry, including the excitations. And in CFT, as you would see, that one would not, obtain a natural split between area by 4G Newton and S bulk. We can see how, by doing this calculation, how these things combine to reproduce the CFT answer. Now, suppose you consider linear combination of excitations, you'll be able to verify how precisely the nonlinear behavior is captured on both sides. And again, by considering linear combination, you can test all these formulas at less symmetric situations. So this is sort of the rough motivation. And there has been an instance, so I think only one instance previous to this very explicit instance, in which this formula has been tested by these authors. They consider excitation primary by a primary operator in a 2D CFT. And it was shown to agree with the FLM formula. And this operator's dimension is perturbative. I mean, it's much less than C, and it was assumed to be a generalized free field. And in the bulk, the excitation is dual to a minimally coupled scalar. Now, what we will do here is basically generalize this observation and extend these the methods both in CFT and to other single particle states, as well as linear combinations of single particle excitations. And in general, all these excitations break the isometries. And in all the cases, of course, just anticipating the answer, So it does make it not as interesting. But in all the cases, the FLM formula precisely reproduces the CFT result. And the agreement actually involves also interesting cancellations between the two terms. Now, in the bulk, yes, yeah, yes.
Getting a CFT answer, and
Yes.
you're expanding that in powers of 1 upon the central charge?
No, in short distance. So I will tell you how the CFT answer comes, and how we'll compare it in the bulk also, finally, yeah.
Central charge expansion.
It's not large central charge expansion. Yeah, it's a perturbative, a small H expansion actually in some. So in the bulk, the agreement will require evaluation of the back reactor geometry to compute this. And also to evaluate this, there is an interesting technique which was developed which we have to generalize. Basically, there is a map from global ADS to Rindler BTZ, which is used. And for that, we need the Bogoliubov coefficient to relate these excitations. Now, in the CFT, entanglement of excitation states, excited states for 2D has been done by many authors earlier. So we have actually streamlined the technique to generalize it and to sort of use it for our purpose. So I'll present that, and I'll present the results. So consider a state in the CFT, say the CFT is on the cylinder. This operator can be a primary or its descendants. And we consider a reduced density matrix. It's on the cylinder, so there is a time slice, and then there is the interval 2 pi x, that same geometry. The path integral in the density matrix form, I mean, if you want to think about it in the cylinder, it's basically there's an operator inserted at t is equal to minus infinity, and an operator inserted at t is equal to plus infinity. And this partial trace basically leaves a cut here. And then computing in replica trick means that you glue these cylinders together. And there is a conformal map. I guess many people know in this audience. There's a conformal map in which this density matrix, this to the power n, this computation can be mapped to a 2n point function, correlation function. So in which these maps, I mean, I'm going over quickly because I sort of think that many people are familiar with this. So 2n point functions on the plane. I mean, you map first the cylinder to the plane, and then there is this, each plane is mapped to the wedge of 2 pi n by this, and the operators go to certain. So here's the geometry after, I mean, so basically this is the geometry. Say this is the n equals 8 replica surface, and the operators at t is equal to minus infinity and t is equal to plus infinity are kept on the circumference of a unit circle. Eventually, this is the eventual geometry, and this is at the length of 2 pi x. I mean, this is the interval length goes to the separation of the operators, and this is the geometry one evaluates the 2n point function. So this CFT calculation at least has a well-defined formulation in terms of a 2n point function correlator, and then taking n going to zero limit. And also, just you have to remember that we are evaluating the entanglement. I mean, this ratio of these density matrices. This is the vacuum. So we are subtracting out the contribution from vacuum. So we will, I mean, when we evaluate this, we won't see the c/3 log term. We will get the extra terms. So so this is the map, and just to be explicit, here are the maps. So the formulation is general. If the operators are primary, it is easy to perform these conformal transformation. If they are descendants or composites, it's harder. But in principle, if you're you can evaluate it if you sort of are persistent. Now, in the 2n point function in general is difficult to evaluate. Only in the case of, say, free bosons or free fermions, you can just get the exact answer. But one can set up a systematic short distance. So this is the interval distance expansion of the 2n point function. And here's a picture of the short distance expansion. I will tell you the formula soon. So the first term, the leading term in the 2n point function is basically when you Wick contract, or you bring these operators very close by, because the distance between these two, they are on the circumference of the unit circle. And this is 2 pi x. And the first contribution is just, you contract these guys, right? You sort of bring them together, because that's the OPE expansion. You bring them together. So that's the leading contribution. Then the sub-leading contribution is the following structure. Where is that? Yeah, it's fuses into identity. And this is when they fuse to, eject out some structure constants and so on, some operators, I'll tell you that. But a picture way of thinking about it is that you take pairs of wedges and you take, operators on this wedge and this wedge and think of them as a 4-point function, right? And sum over all the copies of these, sum over all these pairs, basically. So that's another way of thinking about the next leading contribution. It's a picture way of thinking about it. And here is the formula. The 2 endpoint functions factorize in this manner. You can rewrite them as this short distance expansion in this manner.
These points come close to each other when the interval is made small.
Yeah, it's because the separation between the operators after these maps are the interval size. So they come together, and so essentially the correction is, so this is the identity, and this is the next correction to that, which is essentially a 4-point function. And one can evaluate this, I mean, the first subleading correction arises from this. And once if you know that, you can actually plug this back into this formula and evaluate the entanglement entropy to this short distance corrections. Yes? That is, in the short distance, that is the first. But yeah, if you think about the 2 endpoint function, so x's are coming closer together. So it's a channel, and then it emits, you expand it around the identity channel. So it emits a structure constant times an operator. And this is a way of writing it. That's all. It's a way of writing that, I think. Yeah.
You get 2 pairs because
yeah,
whatever operator you produce has to fuse with
fuse with another one. Yeah. So that's the structure, and this 4-point function can be expanded. I mean, if people know a little bit of CFT, I mean, you can expand it as the vacuum expansion, vacuum block expansion, and if there is a leading operator present in that, you can expand it that way. So this is the leading operator. OP is the sort of sum over operators, so primaries which are expanding it, and this is the first one. The leading one will be the first one. And this is the vacuum block. And the cross ratios in terms of those wedges is of this form. And all these things are known, actually. So this is some hypergeometric function. These expansions start with 1. And the coefficients here are known for the vacuum block. This is a particular coefficient, actually. So it's important to note this coefficient. This is 2h squared by c. And the second one is, so as I said, there is two terms. One is this vacuum block, and one is this exchange of a primary. Okay, and all the things are known in that case. And if it is if we are interested in primary operators, external primary operators, then these conformal transformations are simple. Otherwise, they are more involved, except that you have to just keep track of them. And you can sort of write this expansion in this manner. And the thing is that CFT dependence, the dependence of the CFT is here, for instance, in the structure constants, right? So if you're looking for holographic CFTs, and something which we want to reproduce in holography, so you can look at two cases. Look at generalized free fields in which, the weight of the operator is very much small than C. Then that is one example. And in that case, the exchanged operator, the leading exchanged operator is the composite with dimension 2h. And this number is known. This product of these structure constants is known. It's 2. It is easy to derive this. And the weight of this composite operator is 2h. So that's the leading operator exchanged. And this is for h much less than c. So you recall there was two terms, h squared by c term, which is the vacuum block, and this term, right? So if you look at this generalized free field case, it is this term which contributes. And then the second case is when you consider heavy states in which h is of order c, then it's the first term which comes. So there are two cases you can check with holography. These two are the cases. And we have obtained results for both, but we'll focus, I'll mention sometimes, but we'll focus on the perturbative excitations or generalized free field case. Now, the CFT result, let me just quote it. So if you consider descendants of a primary of this kind, descendants of the primary of this kind, this is L to the power L, right? And if you compute the expansion, this is the structure of the expansion. I think many people might know this for excitations. And this is the sort of the block from the stress tensor exchange. This is the other one, other block. And the way the descendance factor is basically what we call a dressing factor. Sort of this green stuff is the extra terms, an extra factor which comes if you're looking at descendants. And we have, this calculation which we have done, we have verified this by direct computation of the free boson, for which you know the exact twin point function. Now, so consider this linear combination when H and H is there, and for a generalized free field. Okay? So here, OP, that operator dimension is 2H, and the structure constants are known. And then, this is the sort of a linear combination of this, and this is the sort of correction to the entanglement entropy. Again, many people might be familiar with this term. Then there are these corrections, and this is the next correction. Note that this is actually like it's non-analytic. If H is some arbitrary object, it's a non-analytic object. So, so this is the sort of leading expansion, short distance expansion, and these are the coefficients. Now, and this G's, how do you extract the G's? So there's a generating function for the G's. Now, why am I saying these results, right? Okay, one of the tests we have done with these results is that when H is much, much greater than C, we have cross-checked these coefficients against certain, coherent states called Benedorff states. I think these people have evaluated that in gravity, and we have cross-checked these coefficients, which we evaluated from CFT. Now, let me say this is the focus of the state which we will do. Basically, a linear combination of the primary plus one descendant, left Virasoro descendant, say, right? And let's write the entanglement entropy explicitly. So here there is a term of this kind. Again, the modification of 1 minus pi h, which is the usual thing which people know. And you see how the linear combination C0 and C1 feeds in. And there is this term together with this. Our goal is actually to reproduce this result using the FLM formula. Right? This is a CFT calculation. We have calculated this in basically for these generalized free fields, weight H much smaller than C, and we have this result from CFT, and we would like to check it against holography. Yeah.
One thing I didn't understand.
Yeah.
You were calculating this 4-point function, and you said you did it in identity block, and then
identity block plus the. I just wrote the general formula. So this identity block, that means stress tensor and its descent, and stress tensor and its descendant. And that's the first one. And then
this block when these two are brought together like this.
Yeah.
Okay.
Yeah.
So the identity part you'd already
taken into account.
So it's the rest.
Yeah. The identity part is this.
That's the identity.
That's the identity part.
Block.
Yeah.
No, but I'm saying just identity in the identity block had already been taken.
Taken care of. Yes. It's the rest. Yeah.
And the other one, please say what the other one is.
The other one is when one operator is exchanged.
It's a double trace operator.
It's a double trace operator.
And then there are an infinite number of double trace operators.
There are infinite number, but the leading one, O squared, basically, O squared. Yeah. So here is the correction. So this is the correction, and we have an explicit formula.
Justin, you just answered this. So you're assuming that when you're going to do this in the bulk, you're going to assume that the exchange is the gravitons and the single double trace O squared.
So in the bulk, okay, you will see how I evaluate it. I will just go ahead and use that area by 4 G Newton plus S bulk, that formula. So how to compute S bulk, I will show it to you. And then you can come back actually. So single particle states in the bulk. Now, so primary is a global, and its global descendants are dual to a single particle excitation of minimally coupled scalars. So this is the metric of global ADS, and this is a minimally coupled scalar. And the mass dimension relation is the following. Delta is 2H here, and this is a relation. And you can expand these solutions, excitations, in terms of modes. I think everybody knows this. These can be written explicitly. By imposing fall-off boundary conditions and regularity at the origin, actually these modes are quantized. Okay, and this is the formula for the the energy. Here are the and of course you can the commutation relations. These obey the commutation relations, and the states are therefore just creation operators on these, right? And here are the wave functions of the few modes. And these are the states. This is the A naught naught, basically. This is just the primary 2H, and this is the 2H plus 2, the descendants with zero angular momentum, here is the L1, for instance. So the wave functions are precisely known for these modes. And the states are normalized in Klein-Gordon product. And here is the state which we are interested in, a linear combination of the ground state, or the C0 HHH, and this one, okay? And this is what we will identify with this psi naught naught, if you remember, just to remember that. These are the modes. You see there are two quantum numbers, the angular momentum quantum number along the phi, and the radial quantum number n. And A naught naught is the first one, and A10 is this one with the difference of 1. So you can match it with these, this is the identification just from the symmetries.
Descendant number.
Yeah, left hand. N is the total, you see, let's see. Yeah, like N is like total, like L0 plus L0 is total, and yeah. So what do you have to do? So you have to excite this vacuum by this mode and calculate the back reacted geometry. Okay, the methods, I mean, are linear actually. And so once we excite the global ADS3 by this vacuum, then of course there's an energy density, and this will back react because G Newton, we want to keep track of the first G Newton correction. And at leading order, we solve the Einstein's equation with the expectation value of the stress tensor in that state phi. Now, this stress tensor is given by this, right? And we are taking a normal ordered stress tensor here.
So you do this to find the corrected area.
Corrected area. So we find the corrected area and we find S bulk, and then we.
And you don't need to correct the surface.
Yes, at this order we don't need to correct the surface, yeah, because we are working at G Newton and the surface is minimal. Right. So this is the stress tensor. And we just substitute the mode expansions inside and can evaluate the expectation value on any state, for instance. And the thing about it is it's normal ordered, and I'm just mentioning some things about it. So, of course, when you normal order it is insensitive to the UV divergence. And however, this divergence, of course, doesn't depend on the states. It's same for all ADS3 vacuum. And this is because we are interested in the difference between the vacuum and the excited state. So it's sufficient to work with the normal order stress tensors. So we go ahead and evaluate, say, the TT component. All the components need to be evaluated. And here is the expression for the TT component. Note it has time dependence as well as angular dependence. And we have actually evaluated the components, all the non-zero ones, and showed that they satisfy the conservation law. It's just a cross-check for us. And just to see the energy profile of the state, for instance, this is the radial direction. And these are the various weights, for instance. And this is like, I look at time slice t is equal to 0 at various angles. This is like phi is equal to 0, phi equals pi by 2, 3 pi by 2, just to show that there is an angular profile to this excitations. Now,
Sorry, your notation.
Yeah.
Just solving classically.
Classically, yeah.
Finding the change in the metric due to this field condition.
Yeah, so we see this phi is A dagger, this is A naught dagger, A10 dagger, right? Which is a quantized mode of that. Oh, okay. Then you substitute phi inside and then,
Right hand side of the
expectation value.
Because you've got one quantum.
Yeah. You can calculate it reasonably easy, actually. And then this is the profile. And this is just to show that how the profiles are. And then you have to resolve Einstein's equations, back-reacted Einstein's equations with that profile. So this is the ansatz, because it has angular dependence. You can see how intricate it is. It has angular dependence, and all these components can be found. And I'll present J4 because that's the crucial one. And just to see how detailed it is, so these linear combinations are going into that. And there are various coefficients, and it is a detailed function. Now, this metric, of course, satisfies the property that if you read out the boundary stress tensor using the Pfefferman-Graham coordinates, it has to agree with the CFT answer. So it satisfies that. So that's one of the checks we did. And once we have the perturbed metric, we can evaluate the perturbed minimal area. And as Shiraz was saying, that we don't need to correct the Ryu-Takayanagi surface for this. We just substitute, substitute the surface and into the corrected metric and evaluate. This is the formula. And once you evaluate the area, and this is the minimal distance, okay, there was an R, there's a turning point in the geodesic curve, and that is this turning point. And once you evaluate this, this length, here is the length. You have to be a little careful in evaluating it, because you see, this one depends on angle. The metric depends on angle. And you have to be a little careful, because once you go, when phi prime is greater than 0 or less than 0, phi prime is greater than, so you have to be careful. In 2 branches, you have to evaluate it carefully. And this is the trajectory in the 2 branches. And once you evaluate it, this is the formula, this is the answer you get, the corrected area. Now, you get that first term, and the second term doesn't, of course, agree. There's a minus sign here, but this is 4h. And if you see that expression, it's very similar to that. That's 8h with a higher power of this, So it doesn't precisely agree. So of course, we need the S bulk to actually make it work. So yeah, it has the same structure, but not quite there, right? And it should be somehow, of course, if everything is right, you have to evaluate S bulk, and it should cancel this, and it should reproduce the other answer. So how do we calculate the bulk entanglement entropy? So if psi is a single particle state of interest, then the reduced density matrix, psi is this in the bulk now. It's some A dagger A and something. And we need to trace over the remaining part. And once this is performed, we can evaluate the corresponding von Neumann entropy. Now, so it is convenient to go to a coordinate system in which the Ryu-Takayanagi surface becomes the Rindler horizon. This was actually one of the earliest things where I think Rob was involved in this. So then the partial trace over sigma A should reduce to the thermal density matrix. And these excitations would be evaluating thermal endpoint functions. Now, here is the map which we need. So basically, it's ADS3 hyperboloid parameterized in 2 different ways. So this parameterization T phi is the usual one, actually, which gives you the global ADS. We need to shift this phi to make the, I'll tell you why we need to shift the phi. And this is the other one where you go to the Rindler coordinates. I've boosted also by this eta parameter. I can explain reason why. But these are the sort of 2 change of variables. You have the same hyperboloid, but you parameterize it in 2 different ways. So this is the same hyperboloid, and theta was that opening angle. And so once in the other coordinates, in these ADS Rindler coordinates, the metric looks like this. And there's a horizon here with temperature 2 pi. Now, this is the inverse transformation. There is you have to choose a branch, so one particular branch. And that is where the thing is. So the usefulness of the Rindler coordinates is that, if you look at t is equal to 0 slice and rho equals 1, right, which is the Rindler horizon, right, that is the image of the Ryu-Takayanagi geodesic. You can actually show it explicitly using the map, that object is the image of the Ryu-Takayanagi surface, right? Once we make the boost identification, cos eta is this. And the Rindler VDZ, of course, does not cover the whole global ADS, and that is because we have chosen a particular branch and so on. And therefore, we have 2 patches of the Rindler wedges, left and the right. And a scalar field in general in ADS will be having support in both the branches. And here is the expansion in Rindler space with both the branches and with the various commutation relations. And these also are known in terms of hypergeometric functions. And so we have 2 wedges, and the global ADS3 vacuum can be thought of as thermofield double state in the left and the Rindler wedge, okay, with the inverse temperature 2 pi. And a creation operator on the global ADS can be expanded using the Bogoliubov coefficient in terms of the operators on the Rindler wedges. So here's I, which is left and the right. And so these are the Bogoliubov coefficients. So you have to compute them. But once you have this computation, 10 minutes, okay. Once you have this relation, you can relate these operators in the global ADS to that in the Rindler space. And here are the usual thermofield double relations that, if you annihilate, you can create on the left. If you create on the left, you can annihilate on the right. And these are all, basically these operations, the left action on the left wedge can be converted completely as action on the right wedges. And the global ADS3 vacuum is annihilated by these. And for that, the Bogoliubov coefficients satisfy some relations. These are the relations. These are the typical phenomenology of Rindler space. I mean, it's the same thing. And therefore, action like this, A dagger Mn, right, can be expanded in terms of completely the right wedge, and it's of this form. Okay, so using all those relations, we have expanded this operator which acts on the global ADS vacuum in terms of the Rindler wedge completely as right Rindler operators. Okay, since these excitations are in terms of the right sector, the trace over the left sigma bar can be easily done because the trace basically creates the thermal state, right? So the trace can be done, and here is the, suppose it was vacuum, and you do the trace, you will get the usual thermal Hamiltonian with temperature 2 pi. And if it was this excited state, so consider this linear combination of excited states like this. So that's your state you're interested in, a linear combination of excited state with this normalization. Then the operator is this. Basically, I've rewritten that AMN in terms of the Rindler operators, all in the right wedge, by using the various transformations. That's why you get these factors here. And tracing out the left sector is basically, this part gets replaced by the thermal density matrix. So we have the thermal density matrix and acted upon by these excitations, right? And so we need to evaluate basically the entanglement entropy between, particle excitations on the ground state and the CFT. So therefore, we have to evaluate this ratio basically, the excitation and the usual thermal, right? Now, of course, given this formula, you can go ahead and try to evaluate it, and because everything about the thermal state, and you can just go ahead and evaluate it. But but there is a simplification because this is also hard, and the simplification was noted by this people first. So we need the Bogoliubov coefficients and perform the integrals over omega and k, analytically continue over n, and all that. There is a simplification in the short distance expansion. So here is the example. This is the one Bogoliubov coefficient they computed. So these coefficients relate the 0, 0 state to an omega k Rindler state A dagger omega k. And you see that cosh eta, which controls the distance, the interval distance counts there. Okay. Cosh eta is basically here. And if you translate it, cosh eta is like pi x. It's like pi x. So the Bogoliubov coefficient is suppressed as pi x to the power h. Pi x is that circumference length, right? So this is, we have computed other Bogoliubov coefficient, and we have shown that this is true for excited states as well. And in fact, there is a pattern of for this Bogoliubov coefficient. And one can set up a perturbation theory because of this for the density matrix. And this is the first order correction in the perturbation theory. Basically, the sum folded with the Bogoliubov coefficient and the sort of constants which we are, which is the linear combination we construct. And this one is proportional to pi x to the power 4h. And suppose we look at it for this particular excited state and compute it. This is the answer, the first correction. And this comes with a plus sign. And note that correction to the area was a minus sign, and it just cancels that. So it cancels that. This precisely cancels that term. And you go to the next order. You see that, okay, just to see the amount of things that, like you have to do an integral over omega and k in this, actually, one integral. And in the next order, this is the expression for the next order correction to the density matrix. There's two double integrals over omega k, and it's quartic in Bogoliubov coefficients. And if you compute it, this is the answer. And yeah, as I sort of said it before early, it sort of amazingly agrees with that evaluated from CFT. Now, therefore, the LHS and RHS sort of agrees when evaluated in the short distance expansion on this particular state. And we have evaluated it for, sort of 6 low-lying states comparison. I mean, I think Bellin and all did just for the HH and all these states and linear combinations. In each case, of course, it agrees, and there is this precise, nice cancellation which happens all the time between these terms, and it sort of works out. And I mean, one of the things I should say is that in the CFT we have a very general answer completely. but we are not able to do that in the bulk. We have to do it very intricately in this difficult fashion. And conclusions, let me just sort of mention. So the details involving this FLM formula are interesting. I hope it is interesting. And several features of holography are tested. The CFT evaluation of the entanglement entropy of excited states, the use of the generalized free fields, because that thing went in crucially, evaluation of Bogoliubov coefficients, the nonlinearity of the entanglement entropy in the superposition of states. That same structure came out, and the FLM formula as well as this formula in very less symmetric situations. And recently, very recently, just maybe a few weeks ago, I think this authors tested it for higher dimensions, for U1 current excitations and others in higher dimensions. So maybe I'll just leave you with a sort of question. So, so one of the interesting generalizations is to study the entanglement entropy of descendants of just a vacuum. And here is a formula for that, for instance. This is the usual term many people are familiar with, and it gets corrected to this. And these are universal constants actually, and all these are universal numbers. And it will be good if one can actually evaluate the similar, set up a similar calculation for this, because these are universal, and because graviton is topological in 3D, and it will help to understand the graviton as well as this formula better. I'll end with this. Yes, yeah.
Questions?
Yeah.
I mean, this is very nice. Maybe I want to check one thing about the matching. So I would have expected the FLM term, because it's a bulk entanglement, to get contributions from all modes, right? Everything in the theory, all the fields.
Yeah.
Right.
Yeah.
Because you're doing a small distance expansion,
right?
It's only getting contribution from the particular double trace, and that's where it was sufficient for you to look at the corresponding one particle state in the bulk.
Right. Yeah.
But for the example you're talking about with the
gravity, you mean?
With the gravity, and then
that might be
1/c. I think you do need to know about the entire CFT spectrum.
Yeah, the 1/c.
At that coefficient.
But this also one can try. This one I don't know.
I think this will be a very interesting check, because as you say, the formula is nice.
Yeah.
But it would be very nice to sort of see how it comes about.
Yeah. Heavy states, I said one comment, because we tested this, we had this general formula. So for instance, let me give you the very general CFT formula. So this very general CFT formula was here, which involved, I haven't written it down, but I'll tell you what it is. Like for instance, this is a very general short distance CFT formula. And these coefficients, for instance, have a sort of formula, have a generating function, basically. All these coefficients are known. What I'm saying is all these coefficients are known, how it's corrected. So I think Caputa and Pawel and all, they have a sort of coherent state in which they excite all levels using some, certain weights. And that state has been identified as Bernoulli's sort of geometry, actually. And this answer in the if you take their entanglement answer in the bulk and do a short distance expansion, put in these coefficients, it agrees with that.
And if you are in
for the heavy state, for the heavy state.
And if you are in the monodromy regime where H is much larger than C.
H is much larger. Oh, okay. Then this is H is order of C actually. Yeah, I don't know.
Then it creates a conical defect in the bulk.
Okay. Yeah.
Or a black hole.
Right. That I don't know. Yeah. Well, yeah, that's hard. I've just ordered H is of order C. That's what the expansion is.
I'll ask a very vague question.
Yeah.
About this FLM formula, there's something seems unnatural to me.
Yeah.
That is, you're looking at the quantum fluctuations of these scalar modes,
right.
And each different fluctuation would change the area a little bit. But then you just look at the expectation value of the change in the area, somehow decoupling that area change with the modes. Now, with this order, I don't think it would matter. But I was wondering about next order.
Okay.
Whether we have to keep the area as a quantum fluctuation as well.
Right. Yeah, so I think this Bellin and all, they went one higher order in, I don't remember their paper, but they also, higher order in G Newton. Yeah, but somehow my impression from that paper was they didn't correct the area there too, actually.
I
It was surprising.
Area doesn't need to be thought of as a quantum operator.
Yeah, I think they didn't. Yeah, they didn't need to at that order. But the thing about that is they didn't have a check.
Okay.
They didn't have a check. So yeah.
I have a comment about that. I think those things get counted in the entanglement of graviton fluctuations.
But in this three-dimensional case, there are no graviton.
There are edge modes.
So those are sort of universal.
Not edge modes at the boundary, edge modes at the cut.
Okay, good. So how are they counted in this?
Yeah, I don't know. That's what the last problem was, the graviton actually. Yeah. Yeah.
I also have a question. Sorry. Yeah. How did you fix gauge in the bulk?
The gauge?
Like the diffeomorphism gauge?
No, there is. I mean, this is just a scalar in the ADS.
But you calculated the back reaction, right?
Back reaction. Yeah. So we chose this ansatz. Sorry, I should show you this. Yeah. So here's the ansatz. Cited state. Sorry. I'm going backwards. There's an ansatz for the metric. That's okay. That's where you can say there's a gauge. So we chose this ansatz for the metric, and it of course satisfies all the equations. Yeah, here it is. So you see this, when you set these things to 0, it is the global ADS, and this is the corrected one. And these are all, yeah, for instance, here's a solution for that, J4. Yeah.
So I guess the reason I was asking was that I remember, I might be misremembering, but an important step in the Leukoch-Maldacen argument was that the area does not change at leading order because of extremality, even when you change the solution. So but for you used extremality to say the surface won't move.
Surface won't
but
move.
At leading order, you have an area change. I was wondering whether it's actually some gauge choice, whether surface, yeah. Are you working at second order or what's going on here?
G Newton order, same G Newton order. And yeah, we don't change the area, but I mean, we don't change the minimal surface. We just evaluate the change in area because of the metric has changed.
Okay, so do you have an idea about why it's consistent with this step in the Leukoch-Maldacen argument, unless I'm misremembering?
Yeah, but this is what you would do naturally, right? I mean, this is what one does naturally.
Right. Any more questions? Looks like
okay, by the way, I should say Simanti will talk. I mean, there's Simanti who's a postdoc here. She will talk on the last day about the details of the Bogoliubov transformation and how it is, how the perturbation theory is set up.
Loga.
Both on the CFT side, on the gravity side, you have these C0, C1, right? General parameters.
Right, yeah.
So, like you could check, for example, these various things like, is there a way to check something like a first law? Like, for example, there have been these arguments that you can try to derive Einstein equation using entanglement from the boundary theory and so on. In this calculation, is there a way to check it? By just varying C0, how things change or something?
Maybe. Because, yeah, you have a control on the variation. Yeah, maybe.
You think it could be done in this setup?
See, I have to look at that. And yeah.
Okay.
Those arguments are very general, so it will be like application of that.
Yeah, the question is to check those arguments because those are very formal arguments.
Yeah. Even the Maldacen and Lukovic, if you look at their section, it will be an argument, and then then it will be the.
Yeah, but
yeah.
All right. If there are no more questions, let's thank Justin again.